Okay, I will start by a reminder of what we did the first two lectures. So first of all, okay, remember that there is this link that points to a Dropbox folder where you will find the outline with some references and this list of goals, and also some material. So I put a PDF, a scan of my handwritten notes for part A, the perceptron. Unfortunately, the last line is missing because of the scanner. So maybe during the weekend I will try to redo the scan and update the notes. And I will maybe put some additional material. You also find in the outline there is also a list of references. And there is also a draft of the first 3 chapters of a book we are writing, on which this second part will be based. You can take it from the Dropbox. Please don't circulate it too much because it's work in progress. But of course, any feedback you give me or my co-authors on the book is greatly appreciated and useful, because I mean, it's a book that is meant for PhD students. So if you don't like it, it's very bad. So let us know. Okay. So this is the outline for today. Remember that the goals of my this kind of extended tutorial was to bring together things that you have already seen in other lectures. I think we already met the first 4. So I gave you an example of a SAT-unsat transition in a very simple setting, which is the replica, I mean the convex perceptron, where everything is replica symmetric and the calculation is easy. We obtain an analytic expression for the transition point. I illustrated on the way a simple replica calculation, which is the replica symmetric calculation for the perceptron, that is also very similar to the replica symmetric calculation for the p-spin that Giulio introduced, and also to the planted replica symmetric calculation that Florent did. I gave you a vague idea of what is RSB. Federico will come back on that. And I think, I hope now you start to be convinced that this SAT-unsat transition is really very similar to jamming, and Sid and Karen are going to discuss jamming this week. And so what I would like to do today to conclude is to discuss a little bit more the similarity between spin glasses and particle glasses, which has been already discussed by many people, but I'll try to be a bit more quantitative, let's say, and make connection with the problem of packing in large dimensions. So that's the outline. Now, briefly, what we have already done was, okay, we studied the perceptron in the setting of a random constraint satisfaction problem. So we have a variable x on a sphere. This is a kind of spherical spin, okay, like in the p-spin, in the spherical p-spin. But now we want to satisfy some constraints, which are these constraints. These are linear constraints that we want to satisfy. There are m of them. And the control parameter in the thermodynamic limit are the ratio of constraints to variables and the parameter sigma that enters into the constraints. So we have discussed the phase diagram in the plane of alpha and sigma. For positive sigma, the problem is convex. You don't have RSB. This was studied by Derrida and Garner. We have 2 phases. They are both replica symmetric. One is SAT and the other is unsat. We said that in the unsat phase, the energy is basically, the energy landscape is very simple. You just have a single minimum. The system is harmonic. The minimum is at some energy that we have computed analytically that goes to 0 at the SAT-unsat or jamming transition. And below in the SAT phase, you have still one minimum, but now the minimum is flat, and you have a finite volume of solutions that have 0 energy, okay? And so here you have a finite energy and entropy equal to minus infinity at 0 temperature, while here you have 0 energy and finite entropy. By the way, I got many questions on this point of minus infinity for the entropy, and if you're not, I mean, if this is disturbing for you because you think that the entropy is positive, that's true, but the entropy is positive for quantum systems. If you have a classical system, in the 0 temperature limit, just do the calculation for one harmonic oscillator in the 0 temperature limit, and you will see that the entropy goes to minus infinity, just because the volume is 1 point, and the logarithm of, so the volume is 0, and the logarithm of 0 is minus infinity, okay? So if you, I mean, really, if you do just one harmonic oscillator, you are going to see what's going on. Okay, then we did the negative perceptron, and for negative, I mean sigma negative. For negative sigma, the problem is non-convex, and it's like a billiard. So you have it becomes basically you have a sphere, and you have obstacles on the sphere, and you have a particle that is trying to move around these obstacles. And the obstacles are quenched. And then you have a lot of different phases. So let's focus on, we said, OK, let's focus on what happens at very negative sigma. And basically, we have this picture that is the picture that you have on the school flyer. And OK, this is now it's a picture of the energy landscape seen from above. OK, it's like you are here, and you are seeing this space, the space of solutions from the top. You have the energy landscape. OK, so so you have at low density of constraints, you have a replica symmetric SAT phase, like you have at positive sigma. So you have just one bunch of solutions that seen from above is something like a cluster of solutions. And then you have this dynamical transition, like in the p-spin, like in mode coupling and so on, where this space breaks in an exponential number of clusters, each cluster having a finite entropy. Okay? And then you have the Kautzmann transition, where you have an entropy crisis, and this entropy of clusters goes to 0. So you just have 1, 2, 3 clusters, like in the random energy model, just a finite number of ground states of clusters. I mean, the clusters still contain an exponential number of solutions. And then you have the Garnet transition, where these clusters break again into many small clusters, subclusters, let's say. And finally, you have the SAT-ANSAT or jamming transition, where all these things disappear, okay? And the energy becomes positive. This is what happens at very negative sigma. When sigma is increased towards 0, these transitions merge, and you have some zoology of phases, but that's not important for my lectures. So, okay. Now, then we discussed the analogy with spheres, and we said, OK, in spheres, what I can do, I can formulate the sphere problem in a very similar way as the perceptron problem. Now, my variables are n points in a d-dimensional space. I can choose either a cubic volume with periodic boundary conditions, or I can take a sphere in d+1 dimension. And then in both cases, I forgot to write it, what I want to do is that I want to take the limit where n goes to infinity, and the volume of the space goes to infinity, with constant packing fraction, which is going to be the density times the volume of one sphere. So it's the d-dimensional volume of a sphere of radius sigma over 2. And my constraints, which were linear constraints in the perceptron, now are not linear, and they depend on an index mu that is a pair of indices ij. So I have n times n minus 1 over 2 constraints, so for each pair of spheres. And the constraint is just that they should be separated by distance sigma. So the distance minus sigma should be positive. Okay? Now, the problem is that I said, OK, this is the packing problem in d dimensions. And so I want to maximize the density. Like here, I want to maximize alpha. And the problem is that I have two main differences. I don't have any quench disorder, because, I mean, in the perceptron, I have the phi that are random objects. Here, I don't have it. And also, then I have a crystal phase. So if I look, for example, in 3D, this would be 3D, and I look to the pressure, what I get is that I have a liquid phase, but then I have a first-order transition, then I have a crystal, and the SAT-ANSAT, or close packing, or jamming of the crystal will be at 74%. The pressure is going to diverge, and the entropy is going to go to minus infinity, as in the perceptron. But OK, I'm not really interested in the crystal phase. What I said yesterday, 2 days ago, is that, I mean, the jamming point of the crystal is not isostatic. You have more contacts, so it's not critical. So I mean, it's nice, but it's not what you want to study. And it's more or less like the perceptron at positive sigma. OK, so what we would like to study is the continuation of the liquid, and we would like to see how the liquid jams. OK, so in the metastable phase. Now, then we have this problem of disorder. So we have basically 3 possibilities. One is to introduce back some disorder to kill the crystal, and this can be done in 2 ways. Either you add random shifts in the distances between particles. This is the Mari-Kurchan model. Mari-Kurchan-Chakala model. Sorry. You came just at the right time to be cited. So, the second possibility that is more common is to add polydispersity in the spheres. So you put disorder in the sigma. And the last possibility, that is the one I want to discuss because it's simpler, is to forget disorder but go to bigger dimensions. And in particular, if you go to dimension bigger or equal than 4, basically the crystal is killed. I mean, it's there, but you will never see it kinetically. You are never going to nucleate the crystal. And ask Patrick if you want more details. So what I'm going to do today is to focus on identical spheres, no disorder, dimension bigger or equal than 4 if you want. I'm going to look at large dimensions. And what I want to convince you is that basically this problem behaves very much like the perceptron. If you look at constant very negative sigma and you increase alpha, alpha will play the role of the density, and so there will be the same set of transitions. Okay? Now, yes? Morally, yes, but I mean, you are put in disorder in both cases. The only thing is that this is easy to do experimentally, polydispersed particles. This is less easy to do. Is it easier to treat analytically? I mean, these two, no. One is yes. One is basically has the same difficulty as 3, but the problem is that one is not very. I mean, it's nice as a simulation tool if you want, but then if you want to do experiments, putting random shifts in the distances is not so easy. So that's why I'm going to. But okay, let's take. I mean, 3 is the simplest case, no disorder. Yes. Haha, ask Ludovic. I mean, Ludovic discussed this point. I mean, there are, yeah, it's a difficult problem. Let me not enter into this because it will take a lot of time, and Ludovic already discussed it a little bit. So I will tell you in the theory how you can remove the crystal. But in a numerical simulation, how to remove the crystal is a difficult problem. I mean, it should be discussed. Okay, now, there is one thing that I would like to, before proceeding, one important thing that I would like to discuss because it's a big source of confusion, is that in all what I am doing, I'm considering that I am putting the constraints into Hamiltonian. I study the Gibbs measure, so exponential of minus beta h, and then I send the beta to 0. So in the SAT phase, now I want to focus on the SAT phase. What this means that I'm giving, so all the states that have 0 energy are going to have the same probability, and all the other states are going to have 0 probability. So my Gibbs measure is uniform on this space of solutions. This means that the temperature, I mean, this means that the temperature is not really 0 in the sense that the thermodynamic temperature is 0, but you are sampling all the space of the solutions uniformly. So how can you think about this? For example, you can think that you do Monte Carlo of hard spheres. So if you take hard spheres, so you forbid any non-zero energy state, and then you do Monte Carlo, so you move and you sample uniformly all the space. So your spheres are moving, okay? You shouldn't think that your spheres are static because they are sampling the space. The other thing you can do is that you do molecular dynamics with some potential or with hard spheres, and you send the temperature to 0, but you keep an infinitesimal temperature. I mean, what you need to move in this space without going to finite energy. Is this clear? So we are sampling the space of all the configurations of hard spheres uniformly, which is what you do in equilibrium for hard spheres. Okay? So this situation is very different from what Sid has been discussing yesterday, where you have really a thermal system, so the spheres are not moving. They are satisfying these constraints, but they are not exploring all the space of solutions. I will come back to this point, but okay.
Another question.
Yes. I'm not sure. No, that's not. I don't think that's what he said. What he said is that we don't know. We don't know. I mean, the best crystals, the best packings we know, are all crystals with one particle per unit cell, except some rare cases where there are periodic packings with many particles per unit cell, but they are still periodic packings. So we don't know any example of a densest packing that is really amorphous, and basically we don't know. But I will come back to this. Okay? You're not satisfied with my answer.
I think you showed that for like a problem like this calculation. There are many empty space.
Yes. Okay. true, you show that the Bravais lattice cannot be saturated for high enough dimensions, but there could be other lattices with more than 1 particles per unit cell that could be the densest ones. So really, we don't know. Okay. Okay, so now I'm going to discuss. Okay, now there is one last point before I move to the discussion of these transitions, which is, okay, I'm going to study a problem without quench disorder, and I'm going to talk about replicas. So that's going to be strange, right? Because we have used replicas to take an average over a quench disorder. So what can I do if I want to discuss glass states of a system without quench disorder using replicas? Can you remember? So when someone from Paris asks some mysterious questions, what is the answer? It happened already twice. Okay, the Franz-Parisi potential. The answer is always the Franz-Parisi potential. So the Franz-Parisi potential, it has already been discussed by Giulio and by Ludovic. And what it is, you take an equilibrium state that I will call R. You take it from equilibrium. You take a second state that is coupled to R. So there is a fixed overlap between the two states. And then you average over the first. And this will give you the Franz-Parisi potential that has been called V. OK, there is a minus T. I'm going to call it. OK, this is the Franz-Parisi potential, V of Q. Now, you see, to do this, I don't need any quench disorder, right? I mean, Ludovic did it, and he computed it numerically without any quench disorder in his simulations. OK, his system was polydispersed, but you could do it in 4D for a monodisperse. So, I mean, the point is that if you have quench disorder in the Hamiltonian, then you can take an additional average over the quench disorder. But you don't need that. So I can define this object for a system without any quench disorder. And you see that if I want to compute this thing analytically, I need replicas because I have a log. I have the average of a log. So what I'm going to do is that this log, I'm going to write it using replicas. I will not do it explicitly because today I will not do any calculation. I just tell you how it works. So this log is going to be replicated. But you see that basically what's happening is that the configuration R, which is an equilibrium configuration that I'm using to probe the landscape, plays the role of the quench disorder. Because you can think that this is the log of this partition function for the X configuration. And then I'm averaging over some external field that is R, that is coupled to X. And so that's really the quench disorder. And if you have on top of that the quench disorder in your H, you can average over it. But if you don't have it, there is no problem. You can still compute the Franz-Parisi potential.
So we take the function of X, and then we average that.
Mm-hmm. Yes. Where basically R is taken at equilibrium. So R is going to select one cluster. So if you have clusters, R is going to fall in one of the clusters in equilibrium. And then X is constrained to be close to R because if I fix Q to be high enough. And so that it means that X is going to be constrained into the same basin. So in this way, I can compute the free energy of one basin. Okay? This has been discussed already by Giulio and by Ludovic, so please don't ask me to spend too much time on that, because otherwise, I mean, the lecture will be, I'm happy to discuss it at the end, but the only point I wanted to make is that this is a tool that I can use in presence or in absence of quench disorder, and it doesn't make any difference. Very good. So now let's go to the lecture. So the first thing I would like to, so what I'm going to do then is to discuss hard spheres. I'm taking R spheres because this is what is relevant for the SAT phase. So I'm going to be in the SAT phase and to approach the SAT-unsat or gem in transition from density below it. Okay, and I'm going to take the limit of infinite dimensions. And this, okay, as I told you, we have this book that is in preparation, so everything I will say is more or less there. And the study, so what I have to do is that I have to start from the lowest density state, that is the liquid state. So for the liquid state, this has been studied by many people in a series of very nice work by Frisch, Riviere, Klein, Weiler in the 80s. And if you want, there is a recent work by Frisch, Percus, 99 on PRE, which more or less contains most of what was done before, and it's a bit difficult to read, but I think it's the best summary of all these works. So what is the idea? I mean, the problem is, okay, I want to study a liquid of R spheres, and now so this is now my particles versus spins. I mean, it's a bit more difficult than in the perceptron to study the liquid, if you want, the replica symmetric phase, because the perceptron is fully connected. There is disorder, so I take my partition function. I did the calculation with replicas. It was quite simple, and we got to the results. Here I cannot, yes?
So, is this my understanding is the current control parameter for a lot of these serial hacking systems is the volume fraction?
Yes.
What does that mean in infinite dimensions?
It's always the same. The definition is always the same. Sorry, it's written very small there, so I will write it again here. It's just the number of spheres divided by the volume times the volume of a d-dimensional sphere of radius sigma over 2, which actually it goes to 0 if the diameter is 1, the volume goes to 0. You remember that Henri Kohn discussed it. If you have a cube in d dimensions, a sphere is basically going to be something, I mean, that you can draw like that. Basically, it will touch the, in 2D, a sphere is like that. In 3D, if you think to a cube and a sphere, you have a more empty space. In 4D, it's going to be even worse, and so it's going to 0. But that's not really important. As I will discuss in a minute, there is a natural scale for, so the packing fraction is going to 0 in large D. But we have to, if we scale it in the right way, we can study what happens. Okay? You're not convinced?
I'm not convinced.
Okay. I mean, in 1D, a sphere and the cube is the same. In 2D, a sphere occupies leaves some empty space at the corners. In 3D, there are more corners, so more empty space. You keep doing that, and you will see that the volume of a sphere contained in a cube of side 1 is going to 0. But it's really not important. There will be a typical scale. I will do it in a second. So, okay, I was saying, okay, I have to do a little bit more work to discuss particles, because basically it's not a fully connected system. So I cannot just say, okay, let's do... I cannot just say what I said for the perceptron. I cannot just compute the partition function with a saddle point. Okay. So what I can do instead is to do a low density expansion. So the low density expansion is what is called the Virial expansion or Virial series. It's the basic tool of the theory of liquids. And I don't have time to derive it, but it's very simple. It tells you that the free energy as a function of the density. So this is the free energy. If you were at my tutorial 2 weeks ago, or I think Gilles discussed it, this is really, I mean, you can think to rho of x, also Ludovic discussed, rho of x is the basic order parameter of your system. It's like the magnetization in a magnetic system. So this is the free energy as a function of a spatial dependent order parameter. And you can construct it by a Legendre transform. And it's going to be like this. You will have a term that is the ideal gas. This is the density of the ideal gas. And then you have a density-density interaction this function f is called the Mayer function, and is just equal to e to the minus beta v minus 1, where v is the interparticle potential. And then you have other terms. The first term is a triangle. The second term is a square. The next term is a square with this. Then you have a square with 2, and so on. And what does this mean? These are diagrams where basically where each point is a density. So if you have a point here, you will put a row of x. Here you will put a row of y. Here we'll put a row of z. Each line is going to be a Mayer function. So here you will have f of y minus z, and so on. And then you integrate over all the variables. OK? So this first term is a diagram like this, with x, y, and one function f, and two densities. OK, this is a standard result that you find in the draft of the book. You find some derivation. So now, OK, this is in general. So this is for a general density profile. So in particular, this could give you the crystal. If you take a periodic density profile, like in a crystal, then you get the free energy of the crystal. And if you don't want to have the crystal, just take a uniform density. OK? So if you take a uniform density in space, that's going to kill the crystal, and you are going to get just the liquid phase. So that's the answer to the question. I mean, in the theory, it's very easy to get rid of the crystal. Just impose translational invariance, and you're done. So so I take this density and I compute it in the uniform density. I take this free energy and I compute it for uniform density, and I get the liquid. Now, OK, this is for generic dimension. What do we know about this? I made a big mistake. OK. I'm sorry, you are not going to see it. But so what do we know about this series? The first thing we know is that, OK, now let me define a scaled packing fraction. I'm going to define phi bar as 2 to the d times phi. And if you remember the class of Henry Kohn, what he told us is that we have a lower bound. If we look to the packing problem, what we know is that phi bar is bigger or equal than 1, because phi is bigger or equal than 1 over 2 to the d. So this is called the Minkowski lower bound. And it is the one that he proved with a very simple proof by the saturation argument. And then we know an upper bound on this thing, which is exponentially large in d, and it's 2 to the 0.401 blah 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 d. This is the best upper bound that is due to Kabatiansky and Levenstein. And Henry also mentioned it. This is more difficult to prove, but it's proven. OK, so you see the natural scale for this object is somewhere between 1 and exponentially large in d, and we don't know. And this is the problem, right? In infinite dimensions, this is, from the rigorous point of view, this is the best thing we can do. We have an exponentially large window where the best packing could be. Now, what do we know from physics? OK, first thing we know, I mean, it's actually a mathematically rigorous result, but it comes from physics, from physicists, from Leibowitz and Penrose, 1964, is that what we know is that the virial series converges for phi bigger or equal than some number that, I mean, that has an expression, but let me not write it. It's basically 0.144 and something like that. So the convergence radius of the virial series is a series in density, and its convergence radius is bigger than this. So this means that, I mean, for all densities below this one, basically the liquid exists. It's actually basically a gas, but I mean, you have a liquid phase, okay? And you are sure that you have a liquid phase, and you can compute all the properties you want with the series expansion. Art spheres. Now, from now on, I will only be discussing art spheres, identical art spheres in dimension d, and this corresponds to the SAT phase. Okay. I mean, actually, you can prove this bound for the convergence is general, but this is the application to art spheres. So this is nice because this is a constructive bound. The Minkowski bound is not constructive. This is constructive because it tells you, okay, if you want to construct a packing with density below this one, just take a liquid, and you can do it. So in particular, you can do a Monte Carlo, and you will easily converge to some packing. Now, okay. Now, can we do better than this? So the first thing we can do is to look better to the virial series. So unfortunately, I made my blackboard mistake. So the virial series, when you specialize it to you have this ideal gas term. OK, let's write it. You have some ideal gas term that is trivial. And then you have this first diagram, second diagram, third diagram, fourth, and so on. So the order in density. So this is order rho square. This is order rho cube. These three are of order rho to the 4. And now if you look order by order, it's very easy to see that the ring, what are called ring diagrams, are the dominant ones. So basically, every time you add a link to a diagram, you are adding an additional constraint, because the Meyer function wants two spheres to touch. So if you add one Meyer function on top of a diagram, you are going to suppress it, and by an exponential factor. So this means that you can, if you look to infinite dimensions, because the Meyer function is exponential of minus beta v minus 1. So if v is 0, which happens when they don't touch, e to the minus beta v is 1, and the Meyer function is 0. If v is infinity, which happens when they touch, this is 0, and the Meyer function is minus 1. So if you want the Meyer function as this form for our spheres, it's minus 1 when they touch. And so basically, when you do the virial expansion, what you're going to do is that you add to the potential, you add and subtract 1, and then you have 1 plus the Meyer function, then you expand in Meyer functions. So so really, this is OK. I don't really have time to go into the details of the virial expansion. But anyway, the important point is that the ring diagrams then are going to dominate at each order. So I can neglect the other ones. OK, and then if you just look to the ring diagrams, what happens to the virial series? I mean, the ring diagrams are easy to compute by Fourier transform, so you can have an explicit expression for them. And what you find is that the series without the other diagrams has a pole when this is the density, 5 bar. Now it's a series. I want to study the convergence of the series, so I go to complex space. So this is going to be the complex plane of 5 bar. And I have a pole in minus 1, because my series has alternating signs, and the diagrams asymptotically go like phi to the n, to the order. So then what I can conjecture is that the series is actually going to converge in the circle of radius 1. So but this is a conjecture, because the problem is that I have to discard a lot of diagrams to get this. But the conjecture is that actually the convergence radius of the virial series is really 1. And there is also some numerical, there is a nice numerical work on where someone computed the coefficients. And it really supports this idea. But this is unfortunately not proven. I mean, the Lebowitz and Penrose result tells you that you are sure that you converge here, but you don't know. So, OK. So if this conjecture is true, which I believe is true, then this means that the Minkowski bound is also basically the radius of convergence. So it's when the liquid, it's when the virial series does not converge anymore. However, you see that the pole is at negative density. So this is really similar to what you do if you have log of 1 plus x, and you do a series expansion. This is going to be x minus x squared over 2, blah, blah, blah. So the radius of convergence of the series is 1, because you have a pole in minus 1. When x is equal to minus 1, you get a... But this does not... But actually, this function exists even for positive density, right? So... What? No, it's really a mathematical thing now. I have a series, and I want to know the convergence properties. I mean, negative packing fraction makes no sense. It's just a mathematical thing now. So my improved conjecture, I mean, my improved conjecture from the... Which inequality? The first one? So the result of Lebowitz and Penrose is that the series converges for at least this value. But it could be bigger. They can prove that it converges for this value. But what I think, what people think, is that actually it converges in a bigger circle. So they just have a lower bound on the convergence radius. For packing fraction smaller than 0.144, you are sure it converges. So you have a mathematical theorem that tells you that the sphere, that the series converges up to this point. So you are sure it converges up to here. And I conjecture that it converges in a bigger circle. What I also conjecture is that it does not converge outside. This is, for sure it does not converge outside this circle. This is sure because already the ring diagrams are divergent outside this circle. So, but this does not mean that the liquid does not exist, right? Because logarithm of 1 plus x exists for x equal 5, even if the series is not convergent. So the conjecture number 2, and this is really due to Frisch and Perkus 99. You can check their paper. So this is conjecture 1. On this I would really bet a lot, and this may be a little bit less, but I would still bet some money. So the conjecture number 2 is that actually if you look to the equation of state of the liquid, and so this analysis is based on you can take all the ring diagrams, you forget the others, and you sum them, and you can get a closed expression for the free energy of the liquid. What happens? That this is, OK, let's say this is the reduced pressure, which for hard spheres is beta p over rho, sometimes called also compressibility factor. So this is 1 for the ideal gas. So at 0 density, it's 1. And then it's going to grow linearly. So if you want, this pressure is 1 plus phi over 2. And this is the contribution of the first diagram. And then you get plus something, which is the contribution of all the other ring diagrams. So the conjecture of Frisch and Perkus, and they give strong arguments to support, is that this thing is actually exponentially small for all densities that are smaller than some density phi 0 bar, where phi 0 bar is equal to 2 to the power 0.22135d. Okay? So for all densities up to this one, you basically have, you can forget all the diagrams except the first. So this is exponentially big, okay, in D. the Minkowski point is here, is 1. So it means that basically the series is convergent up to this point, but you can continue above it until when you are very close to this density, what's going to happen is that this is going to minus infinity. So you have a maximum, and then it goes to minus infinity, which is strange, right? So, OK. And this happens in a region that is constant times this big density. OK. So then people said, OK, maybe what's happening here is that you are approaching the close packing of the liquid. So that is strange, because you would expect the pressure to go to plus infinity. So if you read the paper of Frisch and Perkus, they say, but maybe there is some subdominant correction that is changing the sign. I mean, the asymptotic behavior here is not very clear. We are throwing away the non-ring diagrams. Who knows? OK? So what you could do is that you can say, OK, maybe we could try to conjecture that the liquid exists up to this exponentially high density, which would be fantastic, because it means that you can beat exponentially the Minkowski bound. And Ricon told you that the mathematicians, the best thing they can do is to improve the Minkowski bound to something like phi bigger than some log, some d log d, with a lot of work, right? And then basically for free here, from this analysis, you say, OK, I can beat it exponentially just simulating the liquid. And I think this is more or less the point of view of Sal-Torquato. He has perhaps slightly different arguments, but this is basically what he's saying. Because if you check what's happening here, what happens is that basically, if you forget all the diagrams except the first one, basically the structure factor is becoming negative at this point, which is why you have this singularity. And this is basically what Sal is saying, that if you can keep the structure factor positive, then the liquid or some amorphous other object should exist. But OK, Sal is not here, so I don't want to speak for him. You can check his he has a lot of papers, so you can check the papers.
So ignoring all the loop diagram that you are doing, like the approximation here. So in the expansion, all the loops are ignored. So
Yes.
The pressure is given by the same calculation we do not see.
It's not really a tree, because here the problem is not a graph structure. But this is morally equivalent if you do the tap equations.
You say that represents the probability that 3 particles are touching.
The loop. Yes, it's morally equivalent to a tree.
The context, and then
No, I agree. It's morally equivalent to a tree. So, for example, if you do the Marie-Kurchan thing where you put random shifts, now you can do it on a lattice, and basically this amounts to say my lattice is a tree. So, no, I agree. The other way to look at it is that if you take a spin glass like you are doing, you do a high temperature expansion. The high temperature expansion, which is has exactly the same structure, and if you stop here, what you're doing is the tap equations. So if you're interested in this, there is a very nice paper by Antoine Georges and the Edidia, 91, where they discuss this kind of high dimensional expansions that coincide with the Virial expansion for the R-sphere problem, and they coincide with the tap expansion for them. It's a Plevka expansion truncated at the second order.
So the mathematicians would complain that this is an uncontrolled
Of course.
approximation, right? And
Yes.
So, right, because we're not, we don't really believe the upper bound, that it's necessarily the upper bound is right, because we're throwing away a bunch of stuff.
No, the upper bound, you mean the Kabatiansky-Levenstein bound is...
No, that this Phi 0
This.
provides an upper bound. That's not necessarily...
No, this is an upper bound. It cannot be more than that.
Is that
For sure, because already if you take the ring diagrams, okay, unless you have some cancellation, okay, no, you're right. The diagrams I discarded could remove this singularity. Actually, but okay, now what I want to say today, which is my point of view, is that actually all this discussion is not really important, because much before you reach this point, what happens? What happens to a liquid when it's dense? A glass transition. So much before you have a glass transition, So there will be some dynamical transition before, much before you reach this point. There will be a Kautzmann transition. And this means that above the Kautzmann point, the liquid does not exist anymore. You have a real phase transition, and you have an ideal glass. And what I think, what our calculation suggests is that you have a transition to an ideal glass, and the pressure of the ideal glass is going to shoot up and diverge at some point, which is what I call the glass close packing. I call it the glass close packing, and it corresponds to the Sat-Sat transition for if you forget the crystal. Of course, there can be a crystal, but I'm not talking about the crystal. So, what is is this clear? So this is the conjecture. This is the result. This is it's conjecture free actually, if you want, but it's the result of the replica calculation. You can believe it or not. So it's a conjecture. And now, yes.
Conjecture 3 is true. Does that mean that conjecture 2 is false?
Yes. So they are mutually exclusive.
But you're willing to bet money on conjecture 2 nonetheless.
Sorry. Let me be more precise. No, let me. I believe that that this is true. I believe what I believe is true is that you can continue the liquid above 1 up to large densities. So the liquid formally exists, but then there is a glass transition, and so the liquid does not exist, but for another reason, not because the virial series is formally has some problem. Like in the p-spin, if you take the p-spin and you take the paramagnetic phase, and you go below Td and below Tk, the paramagnetic phase formally it exists, except that it's not physical because you have a Kautzmann transition, right? So I believe that this is the same situation. You can formally continue the liquid, but because there is a Kautzmann point, this liquid is not physical. So this is my conjecture free, if you want. This part of the curve is non-physical. It formally exists. So why it's non-physical? Because if I compute the Franz-Parisi potential, which I cannot do today, but it's in the notes, it's not a very difficult calculation. Then I get these two transitions, So what I get is that the space of solutions, so the space of configurations of my hard spheres, is like this up to the dynamical point. At the dynamical point, I still have a liquid, but it breaks into an exponential number of clusters. And this, I see this because my Franz-Parisi potential has a local minimum at Q non-zero, like Ludovic discussed. And then I have a Kautzmann point where the clusters are just 1 or 2 or 3. So the configurational entropy goes to 0 here. And then I have an ideal glass. And I can compute the pressure of the ideal glass. And it diverges when I reach this point. Now, why I call it glass close packing is not because I like introducing new definitions. It's just that I wanted to avoid confusion. So it's not the close packing, because the close packing could be a crystal. I don't know. I don't want it to call it random close packing, because what people, usually people think to random close packing as something like you have a thermal spheres, you put them in a box, and you see the packing density that you get. This is not what I'm doing here, because what I'm doing here, as I told you, is that I'm assuming that I'm perfectly sampling all the space of possible states of hard spheres. So I have my spheres are moving, and they are able to equilibrate, so which means that I'm able really to go into to visit all the possible solutions. So it's not, it's different. I will come back in a second on this. Let me just see. Okay. Yes.
Just to get a scale for these values, are these also exponential indeed?
Exactly. Sorry, this was my next point. What is the scale of these things? When I do the calculation, so before I just one little. Okay, let me give the scale. So the result is that the dynamical transition happens at a density that is 4.8 d in the units of phi bar, which means that in normal units of packing fraction is going to be 4.8 times d times 2 to the minus d. So you see, it is much bigger than 1. 1 is the Minkowski bound, and it is also what I conjecture to be the radius of convergence of the virial series. But this is not a problem, because as I said, I also conjecture that the virial series can be continued to exponentially big densities. So this is not a problem. So d is actually what mathematicians get with not too much work. Is the ball bound, for example. You remember that they were the best packing and the ball bound, and this is, I think, d multiplied by 2. I'm not sure, something like that. It's the ball bound. So what you see that what I get here is that you can do better than the ball bound. So you can get to 4.8 d, and you are still in an ergodic liquid. So in principle, if you do just a simulation of your liquid, you can equilibrate easily up to this point. So it's a constructive thing. I mean, OK. Then, what's the scaling of phi k? The scaling of phi k is phi bar k is d log d plus subleading terms. So without the bar is going to be 2 to the minus d times d log d. So it's still not exponentially larger in d than the Minkowski, but you get a d log d, which is also better than the d log d that the mathematicians get with a lot of work. This would be also nice. I mean, it's still a very small improvement, right? Still talking about logs instead of log. And then the phi GCP, it has exactly the same scaling. It's still d log d plus subdominant corrections that are a little bit bigger than phi k, because they are not. So that's the result. You can find it exciting or disappointing depending on the point of view. The disappointing thing is that I think that with liquids or glasses, you cannot improve exponentially the Minkowski bound. So maybe Sal is right that you can still have some other thing that is not the continuation of a liquid or a glass. There is some crazy disordered stuff that you are never going to find just by compressing the liquid. And this may be exponentially big. So I don't know. But still, I mean, I think if you just compress a liquid, so if you compress and you try to equilibrate, you are going to stop here. If you allow an exponentially large time in n, you can beat the dynamical point, right, as was discussed by everybody, I think. So if you allow an exponentially large time in n, you can sample the clusters and you can arrive up to the Kautzmann point. At the Kautzmann point, you are stuck. You will be stuck into the ideal glass, and you will get to this glass close packing, and you will get here. And that's the best you can do by compressing a liquid, even with an exponentially small rate.
What would be missing to make this rigorously?
A lot of work, really a lot of work, really a lot of work. There are two problems. The first one is that already making rigorous the statement that you can keep the liquid up to this point is a very big problem, because the series is divergent. So you have to do an analytic continuation of a divergent thing. This is doable, but you have to study the behavior of all these no-ring diagrams. I mean, to my knowledge, nobody tried. But it's really, I think it will be really mathematically very interesting problems, but OK. There are not so many people that still work on this. I mean, there were a lot of people working on this kind of problems in the 60s, but now it's a bit less. So that's the first thing. And then if you want to be sure that you can go above that, then you have to study the Franz-Parisi potential, which means you have either to do replicas, but okay, making replicas rigorous is very hard, or find some fancy technique like the Guerra interpolation method that Florent discussed. It's really hard. So anyways, okay, so this is the result. And now, and now what is missing is that there is also, like in the perceptron, so you see now it's really like the perceptron. I have replica symmetric phase. I have this dynamical 1RSB phase where the Franz Parisi has a local minimum. I have a Kautzmann, an ideal glass phase, and then there is this Garner thing. So somewhere here, there is also a Garner transition, where these things are going to break into a full RSB structure like I get in the perceptron here. Okay. And this is the phase diagram. Now, there are two more things I would like to discuss. So I'm sorry, today I'm not pointing to the outline, but more or less now we are here. Okay. So we discussed the general problem. Now we are discussing the spheres in infinite dimension. I discussed the liquid. Now I discussed the transition densities and how they scale. And now there are two last things I would like to discuss in the last half an hour. One is what happens when you go out of equilibrium, which for the moment I've never discussed, not even in the perceptron. And two, the criticality of jamming. I will be sketchy now because I've been sketchy since the second lecture, but okay. So out of equilibrium. Now this discussion is general, and this discussion is general, and then I will specialize the spheres. So do you remember what Florent told you when he was talking at the end of the last lecture about the state following technique? So if you have a p-spin, you have in equilibrium you have this kind of situation, right? You have Tk, you have Td, and then you have maybe some Garner point here, and this is the equilibrium state. The point is that, okay, if you know that if you cool, even if you cool exponentially slowly, you can go beyond the dynamical point where the system has all these clusters, but at some point you're going to be stuck in a cluster, in a state. And then you can follow this state, and it will give you a curve. And there will be many curves depending on where you get stuck. Okay? So you can prepare your system in equilibrium at different, I'll call them TG. This will depend on your cooling rate, and then you get stuck at different levels. In mean field, you get stuck forever. In finite dimensions, you still can jump out. And this plot was shown by Mark Ediger in experiments, was shown by Florent in constraint satisfaction problems. It's kind of was shown by Giulio. So in particular, in the p-spin, I think Giulio also did the calculation of the, in his second lecture, when he did the calculation of Benarous and co-workers of all these lines explicitly. Yes? The? It's where the complexity goes to 0.
But not when there is zero entropy.
No, the total entropy, the states can still have some internal entropy, but it's like in the REM. I mean, at some point you just run out of states. Okay. Okay, so this plot, I think you have seen it many times, and I hope you digested it. And so this can also be applied to the problem, to the perceptron or to spheres, with a small difference that here I was talking about a landscape like this. So here the energy landscape that everybody had in mind was something like this, right? Where you visit different states, and all these levels correspond, for example, to be stuck in one state or in the other state. But now I am in a constraint satisfaction setting. I am in the SAT phase, so I'm here. So my landscape is not at all like this. My landscape is like this. I have states with, okay? I have, and what I'm doing is that I'm excluding, okay. whatever. I mean, I'm excluding all the states that have positive energy, and I'm looking only to the states at 0 energy. But still, I have many states. Okay? So what happens if I start compressing my Earth spheres, and I go and I reach the dynamical point? I'm going to get stuck into one of these states. Okay? And now, what happens now? So let's say I'm stuck here in this one, and I cannot go out. I mean, I can never go out by jumping barriers, right? Because I have Earth spheres. So I'm forbidding completely the positive energies. But if I am below the dynamical transition, all these things are connected. So in 1D, it's impossible to draw it, but I have, if you look from above, in the picture of the clusters, you have connections between these clusters. So you can go from one to the other, staying at 0 energy. When I reach dynamical transition, these connections close, and I'm stuck in one of these things. Now, suppose I keep compressing. What happens? That maybe this one, maybe the one I'm stuck in, could disappear. So maybe this thing will evolve. Here I'm increasing density. This thing can close. And maybe this can become like that, just a point. Okay? Can you see? And maybe at the same time, these ones are still existing. So what does this mean? It means that if I'm stuck here, at some point I'm going to jam. But I'm going to jam because I'm out of equilibrium. If I could visit in equilibrium all the states, I would see that there are actually other states that are still there. So this means when I'm increasing density, some of these clusters are killed, but some of them are still there. So if I'm able to jump everywhere and to sample everywhere, I can keep going until I reach the ideal glass, at which I really have just one cluster. So the only thing I can do is to continue follow that cluster. But if I'm out of equilibrium, I could get stuck before. Okay? Is that fine? And you see that if I restrict myself to one state, this one, I can undergo a jamming transition like the one that I get in equilibrium, except that I'm restricted in one state. So this gives us a phase diagram like this. Now I'm going to change a little bit the drawing just to make connection with the one I have. Let's do it in 2 steps. Oops. The first step is to reverse the pressure. This is just for convenience. Let's reverse the pressure. So I put here density, but I put here 1 over pressure instead of pressure. So why I'm doing that? Because in this way it's easy to draw the infinite pressure lines. So this is my equilibrium. Here I have the Kautzmann point. Here I have the GCP point. And somewhere I have the dynamical point. So it's the same as above, but I'm inverting. And now if you want, I can also rotate by 90 degrees. And this, maybe I think it's how Ludovic presented this plot for his Earth spheres. So when I rotate by 90 degrees, what I get is here I get 1 over P. Remember that P is beta P over rho, so this is going to be T over rho divided by the actual pressure. This is the reduced pressure. And this is going to be when I do this rotation, this is going to be density, but it will be inverted. So let's put here 1 over density, which is volume, specific volume. So if you want, this is going to be a specific volume versus temperature plot. That is really what Mark Ediger has shown, and also Ludovic. And it would look in this rotated version like this. So you have Phi K, you have Phi D, and you have here this phi. Sorry, this is now it's PK, it's or TK or whatever. I mean, it's pressure, and this is going to be infinite pressure, and this will be phi GCP. And now it really looks like the P-spin. Okay, except that the interpretation in terms of landscape is totally different. Okay, this P-spin thing is in a landscape like this, where all states have positive energies, and that one is for a landscape like this, where I'm focusing on the zero energy line. Okay. And now, so what you know is that I get stuck here, and then I have lines like that, which here are lines like that. So for a given phi g, I will get out of equilibrium. I will follow my state as much as I can out of equilibrium. At some point, my state will jam, and now its energy will become above this density. My energy will become positive. Still, I can have other states that have zero energy, but my state is jammed, which corresponds to pressure going to infinity, entropy going to minus infinity, blah, blah, blah. So you see that depending on the state in which I start, I have these lines, and I get different jamming points. So I get what people call a J line. This is going to be a J line. Okay? Which is exactly the same thing as the zero temperature line of the P-spin. And this is what has been computed by Giulio in his second lecture, where he computed all the minima of the P-spin as a function of energy. And he told you that that these ones have zero complexity. They are not exponential. And when you raise the energy, you have a complexity. And here is the same. The GCP state corresponds to zero complexity, because it's the one you get from the ideal glass. And all these others, when you fall out of equilibrium, here you have an exponential number of possible states in which you can fall out of equilibrium. And all of them can be followed to jamming. And all of them, so you will have a complexity on the J line. Okay, so the complexity on the J line will look like something like this, where this is phi GCP, and this is something. I don't know how to call it. We gave to this thing many names in depending on the papers. But it's, I mean, let's call it phi JD, is the jamming point that corresponds to the states that are created at phi d. Now, this computation can be done. So this would be here the J line, okay? The calculation of these equations of state can be done using the Franz-Parisi potential. Ah, sorry, Sid. No, they're not exactly parallel. They're actually not even lines. They're a little bit curved, but they don't cross. No, they don't cross. Don't ask me why. There is not a real. I don't see any reason why they shouldn't cross, but they don't cross, right? There is no model we know where these lines cross, but there is no reason. I mean, in principle, they could cross. So this calculation can be done using the Franz-Parisi potential. None of us was able to really illustrate it. I mean, I think we all sketched it, but the idea is really simple. Now I think I erased the Franz-Parisi potential, but the idea is really that you should do. Okay, yes, it's true. In some cases, they can all converge to some point at zero temperature, for example, but they don't cross. So I was saying that you can do this calculation. Okay, in the P-spin, you can do it in a very simple way, but in general, you can do it by the Franz-Parisi potential. You just have to generalize the Franz-Parisi potential to have two temperatures or two densities, one for the reference replica that you are using to create the states, and another for the coupled replica that you are using to follow them. But okay, I cannot enter into the details of that. But so this calculation can be done analytically in infinite dimensions. And what you get, so you get this J line. This value, by the way, I told you already that the phi GCP is d log d, so the end of the J line is d log d in units of the phi bar, while this one is like, if I remember well, is something like 7.2 times d. So this is 4.8 d. So you get something, and this line is very big because it goes from d to d log d. So it expands when you increase the dimension. Okay. Yes. What happens above GCP is that, if you want, the states that you can construct starting from some liquid equilibrium and then going out of equilibrium following the basins don't exist anymore. There are no more states above this point, because this is the densest liquid you can make in equilibrium. Here you fall out of equilibrium because there is no more complexity. You follow this state, it will jam here, and then it's over. Maybe there could be a crystal at bigger densities. There could be disordered things that are not obtained in this way. I mean, there could be some crazy state that is somewhere in the landscape that I will never able to sample by using some equilibrium, some compression from equilibrium. So I cannot say anything on that. I can only say that, okay, if you compress the liquid, this is the best thing you can do. That's the last point. So now we have our phase diagram. And this is the last thing. So if I get out of equilibrium, I have this J line. I have all these packings. I can compute them by Franz Parisi potential. I forgot to say, the Franz Parisi potential is really based, the calculation of the Franz Parisi potential is really based on the virial expansion, where you cut at the first virial, like for the liquid, except that you have replicas, so your particles are not just one atom, but there are copies of your atom, so you have molecules. And then what you have to do is just to do the virial expansion. You truncate it like for the liquid at the first diagram, and then you have to treat these molecules, which you do by in the infinite dimensional limit by basically using the central limit theorem. So it's really I would say a simple calculation, and I think in the book, after a lot of work, we managed to put it in a very simple way. It basically makes 4 pages. So if you are interested, just check the Dropbox. There is the book. There is a discussion first of the liquid, and then there is a discussion of the Franz Parisi potential in infinite dimension. And it should, I mean, my hope is that it should be readable without too much effort. If it's not the case, let me know, because it's useful to know. Now, the last thing is exactly, what about isostaticity? So what I told you is that in the there was some question? No, okay. In the perceptron, I told you that if you have a replica symmetric jamming, then the system is not isostatic. It's actually hypostatic in this case. But I told you, boy, it's like the crystal. I mean, the crystal is hyperstatic, but still it's not critical. In both cases, it is not critical. However, if you go to negative sigma, then now the jamming line falls inside the full RSB region. So at jamming, the system is described by full RSB solution, and then it is isostatic. Now, I'm not claiming that you need full RSB to be isostatic. There are examples where you are isostatic and you're not full RSB, but at least I mean, in this model, it always go together, and actually also in the spheres, because what I didn't tell you is that there is, on top of all this, there is a Garnet transition. So I already told you that here there was a Garnet transition in equilibrium, and actually this becomes a line like that. When you go out of equilibrium, you can still define a Garnet transition. So all this region is full RSB, and here is the same. So all this region is going to be full RSB. And this is very similar to the Ising P-spin model, not the spherical, because the spherical has no Garnet transition, but in the Ising P-spin you really get the same thing. And this was a paper by Ising P-spin. this is a paper by Federico and Andrea Montanari, which I think, to my knowledge, is the first paper where they discuss the Garnet transition out of equilibrium, because the original Garnet paper was about this point. And then they extended it to, OK. So then you see that all the J line falls into the full RSB phase. And so as a consequence of this, so now I get to my last point, criticality. As a consequence of the full RSB, and this is this now is a lot of calculations, but you find the there are no more white chalks. Okay, there is one. You find the calculations in the perceptron. I mean, okay, there are two places where you find this calculation. One is the original paper that is a paper by Patrick, myself, Jorge Kurchen, Pier Francesco Urbani, and Giorgio Parisi, which is very hard to read. I'm sorry. It was the first paper. We were doing the calculation. We did many mistakes. We changed the paper many times. It's really, don't try to read that one. But it's the first paper. And actually, I think it's better written in the perceptron paper. The calculation for the spheres and the perceptron are very similar. So perhaps you can look to the paper, the SciPost paper on the perceptron that I mentioned, where we show how can you do this calculation. And it will be in the book, but for the moment it's not yet written. So, okay. So basically, what you have to do now is that you have to analyze the full RSB equations. You remember that, okay, I told you that in the replica symmetric case, what we had here is that Q was the overlap between the spheres. So Q was equal to 1 in the unsat phase, because you have just one minimum. And then at 0 temperature, all the replica go in the same place. While Q was smaller than 1 when you were in the sat phase, because there was a finite volume. Now I have to do the same thing. So I have to approach this line where Q is going to 1. The only problem is that I'm in a full RSB phase, so Q is not, there is not just one Q. I told you there are many Q. There are the Q that describe the inside of the clusters. There are the Q that describe the distances between clusters. So Q is actually a function. I didn't have time to talk about that, but here you have really a function Q of x. And the jamming limit corresponds to the overlap of the smallest, I mean the biggest overlap, or the smallest distance, the one of the smallest clusters going to 0. So you have to analyze, you have a set of integral differential equations for this function Q. You have a limit where Q, the function Q, as in one point is going to 1. And then you have to make a scaling analysis of these integral differential equations. It's not very hard. It's just you have differential equations. You have a scaling limit. You have to make a guess for how it is, and then you check that it is the right guess. And what do you get? So you get several things. First thing is that you get the system is isostatic. So both in the perceptron and in the spheres, you get that everywhere on the J line, independently on the density at which you are always isostatic. So this is very nice, because the first thing we did historically was when we did not realize that there was a Garnet transition. So we just did the calculation as if it was as if it were no Garnet transition. And in that case, you get still a J line, but it's not isostatic. It's hyperstatic. So we were really unhappy. And this was really a big motivation to find the Garnet transition and understand that. So with taking into account full RSB, it's isostatic everywhere. And the second thing that you find is that now if you look to your jammed states, so when you are at the jam states, you have your constraints H mu, and some of them are saturated, which means that in the sphere case, you have two spheres touching. Not all of them. For example, this one and this one are not touching, right? And even if you can have a situation like this. So this one and this one, they are not touching. So this one, they have H positive, This one, they have age 0. And in the perceptron, it's the same situation, except that they are not, h are those functions. So what you can do, you can look to the probability distribution of this h. And this will have something like a delta peak, which describes the contacts. And the weight of the delta peak is basically the isostatic number, which for spheres is 2D, and this was described by Sid yesterday, that you can count the constraints and you get this. But on top of that, you have some background. So if you want, you have your rho of h. By the way, in the sphere case, rho of h is basically the pair distribution G of R. It's just a change of variables. So you have a delta peak in 0. But on top of that, you have a power law. So you have a background. And your background is diverging with some exponent. So maybe, I don't know if maybe Sid is going to come back on that. But OK, you will see. We will see. And OK, so you have this exponent gamma. OK? And the third thing you get is that now you can look to the forces. So every time you have a contact, you can define a force. This is a bit tricky, because if you have hard spheres, OK, the force is 0 or infinity. But what you can do is that you can suppose that these are soft. You inflate a little bit. Then you create an overlap. Then you create a force. Then you send back the sides to the original one. And you take the force divided by the average force, which is going to 0. But you can still, the force divided by the average is going to have a finite limit. And you call this the force. Actually, there is a very nice algebraic structure behind this, which in the end tells you that these forces can be reconstructed by just knowing the contact matrix. And this was, I don't remember who did this first, but we have a paper where there is an appendix where this is described in detail. So if you want to look at it with Eric and Patrick and Giorgio. So basically, these forces come, if you know the contact network, you know the forces. And if you know the forces, you can look to the histogram of the forces. And what you find is that this is a power law at small forces. So you have P of f looks like that. And at small f, you get the power law. OK? So you have, if you want, you have very small gaps that display a critical behavior with an exponent. And you have very small forces that also have a critical behavior. And you can compute these two exponents analytically, and you get numbers. I mean, theta is something like 0.42. Gamma is something like 0.141. They are not equal. This continues in some way, and this continues in some other way. There is also a third critical exponent that I don't have time now to describe. It's in the papers. So we have analytical results for these things. And now there are two things. One is that Mathieu Viard and co-workers have a very nice set of papers where they show that if you assume that you are isostatic and you make some additional assumption, like that modes are extended and so on, then you get a scaling relation between these two exponents, which I don't remember, but it's something like, I don't know. I write some random thing, but it's something like that. Anyway, you get the relation between the two exponents, which is exactly satisfied by the results we get in the replica calculation, which is non-trivial. Theta is 1 over 2 plus gamma. Thank you. Very good. And they also get another scaling relation for the third exponent that I didn't introduce that also works fine. And this is really non-trivial because the replica calculation in principle does not know anything about the scaling arguments that they made. So it's really two disconnected things in principle that converge. And the other, I think, nice thing is that these work very well with numerical simulations. So if you, I mean, I will not write it in the blackboard, but if you prepare packing on the J line, so if you start from the liquid, compress, reach some point, measure these two distributions, you really get numbers that are compatible with this, with, I would say, something like 1% or 2% error. And this is true in all dimensions from 2 to infinity. I mean, we tested from 2 to 12. And I think Sid also will discuss that. I mean, they also have some very good argument that this should be true, and that there is some kind of lower critical dimension of jamming that is 2. That's what I wanted to say. Two last comments. One is that, surprisingly, this is also true. I mean, until now, as I told you, I'm thinking to a setting where you are doing hard spheres, you are doing Monte Carlo, you are sampling very well the liquid, you are compressing slowly, at some point you fall out of equilibrium, you get an hard sphere glass, you jam, and all this works. Very surprisingly, this also works if you just take completely athermal spheres, just drop spheres at random, then you compress them without any movement, so you are not sampling this space. You are really doing some totally different trajectory. You are starting from 0 density. There is no pressure because there is no equilibrium. You're just doing some path here that is bringing you somewhere. Actually, we don't even know in infinite dimension where you would exactly go. We think that you are going to stop somewhere before this point. And OK, this is a complicated thing that I'm happy to discuss in private if you want. But anyway, there will be some other jamming point here that corresponds to the totally athermal procedure. If you want, this is in the P-spin. I think Laetitia maybe mentioned it. If you do P-spin and you start from infinite temperature and you quench at basically 0 temperature, so you do the same thing, you are going to stop at some state that is here, that is called the threshold. And there are ways to compute the threshold by dynamics, by replicas, and blah, blah, blah. So, I mean, but this is something that we didn't do in infinite dimensional spheres. Anyway, what is surprising is that this one also has exactly the same critical exponent. So this exponent seems to be really robust. And this is something I personally do not totally understand. I mean, already in field, why they are so robust, it's strange. Or, I mean, it should be understood better. And why it works in 2D, that's even more mysterious. So this is, I think, where I would like to stop. Now, just a few things. So I hope I achieved my objectives, which are, you have seen, OK, the connection with packing in large D should be quite clear now. The particles versus spin, you really see that basically you arrive to the same kind of phase diagrams using the same methods in P-spin glasses and in our spheres in infinite dimensions, with the only, where I mean, if you want, the central object is really this Franz-Parisi potential that allows you to compute these phase diagrams with quenched disorder or without quenched disorder. Okay? I would like also to mention that there is another method that is due to Monasson that I forgot to mention. There is a very, very nice paper by Monasson, 1995, where he has another way, which is not, it's a bit different. I mean, you can check it. And it allows to, for example, to compute this threshold point in the P-spin. So this was the first thing I wanted to mention. The second thing I want to mention is that you can also redo these calculations in 3D by an approximated theory. And this was introduced, I think, first by Mézard and Parisi in 1996. And then there are many works on that. And basically what you do is that you keep more diagrams in your Virial expansion, but then you do approximations, because of course you cannot do exact things. And in the end, you get some theory that behaves exactly like this one. So it's still a mean field theory if you want. It has the same critical exponents, the same qualitative structure. The only thing is that you can get numbers. You can get true numbers for these transitions in 3D. Oh, but the problem is that you have to do approximations like Perkusiewicz or things like that, you know, if you know liquid theory. And these approximations typically have big error bars, like 10%. So if you want, you get numbers here, but they have an error bar of 10%, depending, not a statistical error bar, but really a theoretical error bar because of the approximations you're doing. But this is a bit in the spirit of mode coupling theory. You know, mode coupling theory, as Dave discussed, is an approximation in 3D. uncontrolled. And here you can do the same thing. You can do uncontrolled approximation in 3D to get numbers, with the advantage that here you can do the approximations that are uncontrolled in 3D but become exact in infinite D, so you have control on that. And if you want to check, I think the best reference to check this is either I have a review on that with Giorgio Parisi, so it will be Parisi and myself on RMP 2010, or there is a more recent paper which is updated by Manja and myself on PRE 2016, and then of course I also encourage you to check the original papers by Mesar Parisi that are very nice. That's it. Final things. Really final, but this is not about science. Florent showed you a very nice slides with the Eiffel Tower. I'm not using slides, so I'm going to draw the Eiffel Tower. And the message is the same. This is the Eiffel Tower, something like that, more beautiful than that. The message is, okay. I should have used slide, I'm sorry. Let's try to do it better. Is it something like that, right? Okay. Okay. So it's the Eiffel Tower, I believe, right? And it's very beautiful, and the message is that it's the same as Florent. I have postdoc. So if you like these things and if you want to work on these things, there are postdoc positions. I plan to open 2 positions in October, let's say October 2017, to start in fall 2018. So if you are interested, please check my web page. And the very last thing I want to say is that I wanted to stay until the end of the school. I'm really enjoying the school. I shouldn't say that because I'm an organizer, but unfortunately I have to leave tomorrow for some little familiar problem, nothing serious. So I will leave. So today I'm here if you want to discuss. I will stay until the end, and I will be at the poster session. But I will leave then, and I would take this opportunity to say that I really enjoyed the school. So I would like to thank Leo and Dakota for doing all the hard work, and I would like to thank my co-organizer for doing some softer work that was, I think, nice. And I would like to thank all the lecturers, because I think they really did a nice job. But especially, I really think that you look really a very good class. You are asking a lot of questions, which is nice. You look interested, so that's nice. So thank you, and thank you for your attention.